Good morning, everybody. I hope you woke up very well and you slept very well too. Uh, well, this weekend, I think you had the ceremony of graduation. So congratulations to those who have friends who graduated. And hopefully next year we will see all of you guys there. So for today, we don't have a quiz, mainly because we have a lot of stuff to do, right? So we're going to have to finish the last lecture, which should take us less than 5 minutes. And then we will have to start on the image features lecture, which is quite a lengthy lecture and might need some time. And hopefully 10 minutes before the end of this lecture, we would make like a revision of all of the things that we have seen so far. It would be quite useful because most of the things that we will see in the future are highly connected with the concepts that we have seen before. So it would be nice that everybody at least remembers a minimum amount of information about every lecture, right? Let's open the others. Yes. Just a few words about the course in general. Yesterday, we met with Karam and we have decided on the assignments details. So hopefully during the lab, Karam would give you the proposed, what is it called, assignments timeline. And you guys will have the ability to ask as many questions and to propose some differences. Basically, so far what we have decided is that today we will give you your first assignment, and then we will give you 10 days to finish this one, 10 or 11 days. Yeah. And then we will have the second assignment. Sorry. We will have the second assignment around the 6th, so basically next week, right? And we will give you your homework on the next lecture. So basically not your homework, we'll give you your project details on the next lecture, and the project will have around 1 month, right? So you're going to have 29 days in total where you will be working either in a group or on your own and trying to basically implement an idea, a larger scale homework, you can think of it, right? Where you don't have any limitations, you don't have any guidelines. All you have to do is just make something work and tell us how you did it. The midterm is going to be on the 13th of September. So basically after 2 weeks. And yeah, assignment 3 should be 1 week after that. So basically the 20th. And the final week, you're going to be mostly working on your project because I know you will not start working on it as of this week. The final exam is going to be on the 6th of October. So we decided to basically give you guys a simple revision, one for the lab and one for the lecture, where we basically just go through the lectures again and highlight what are the important concepts that you're probably going to see during the final exam. Yeah, and I think your friends are already here, so we can start. By the way, you guys can hear me very well?
Yes.
Perfect. Nice. So let's continue. Nice. Let's share the screen. So yeah, last week we spoke about the object detection lecture. And in this week, we spoke about different things. So first one was connected components and how to do connected components labeling. We saw that it's a very basic algorithm, similar to a clustering technique, you would think of it. And then we spoke about object detection and how we could implement it using template matching, how we could improve it a little bit using image pyramids, and how we can definitely make it much better using the histogram of oriented gradients, right? And then final part was the active contour models, which is just like an extra bonus part of the lecture. So just for a quick recap, what is connectivity? So connected components is something that is defined using the relationship between pixels that are connected together. So we have the 4 neighbors component, or the 4 connected neighbors. They look like this. This is what we care about. And we have the 8 neighbors, basically everything that you can touch. So a connected component would look something like this. I think we should zoom in. Sorry. Nope. Oh, wait a second. I'll just open it on this one. So yeah, maybe Microsoft Edge is better. Nope. Well, looks a bit better. Yeah, sorry for the break. So basically a connected component would look something like this. So here, in this case, where all the pixels are connected together using this 8 connected component, we can see that all of these pixels are in some way or another connected with each other. But if we use the 4 connected component, we see that they are not. So we did this example where we just went through the image and we connected all of the parts which are connected together. So here we saw that all of these pixels contain 0. So we just, yeah, all of these pixels contain 0. So we don't care about them. And then we saw the first one. We saw that it's not connected to anything else before it, and we gave it a new label, 2. Then we went for this one, 0. This one, not connected to anything. We gave it a new label, 3, 0, 0, 0, 0. We have 1 that is connected to this one, so we gave it the same label. This 2 connected to this one, we gave it the same label. This one connected to 2 classes or 2 labels already, and we can give it any label we want. So let's go with 3 or 2, as you wish. This is a 0, 0, so we don't care about these. 0, 0, we don't care about these. We have a 1 here that is connected to a 2, so we put 2. Finish the image, all of them are zeros, we don't care about them. And then we have the second pass where we're basically merging the labels which are connected with each other. So here we can see that 3 and 2 are connected with each other. So we merge them into the same label. Either we merge them into 3, we merge them into 2, or we merge them into a 4th label. No, it doesn't really matter. So yeah, let's finish this. Yep. So this is what connected component. Yep. So this is the connected component labeling part. Now the object detection part, we started it with a simple algorithm or a simple approach. Sorry. Yeah, with a simple approach of template matching. Basically what we have is a template image and a source image or a list of source images. And we will go through these images to find where in these images is the template image located or something similar to the template image located. So one problem that you might have found with this one is that if we rotate the image a little bit or we look at it from a different point of view, this template matching algorithm will not be working. So how is it built? It's basically built on the pixel similarity distance, right? So either using the MSE error or using the cross correlation error. They decided to improve this a bit further by using image pyramids to work on basically the scale or the size of the objects. But again, it's very sensitive to the orientation or to the point of view of the object. A very good application of this one basically would be image analysis, right? Or not image analysis, medical image analysis, where we have like, yeah, let's give you the scenario that worked on. So we have hips like this, the human hips, sorry. So the human hips, they look like this, and we are always taking the MRI scans from the same point of view. So always we have the same components or something very similar to it in looking. And the main difference between the different patients is how or what is the size of their bones, right? So basically, if you manage to do something which is irrelevant or invariant to size or to scale, then template matching or image pyramids, using image pyramids is a good algorithm for that case, right? So why do we, or like a small trick, why do we make this blurring before we do some sampling? Is because if we take one random pixel from this 4x4 place, we're not sure that the pixel that we took kind of represents that 4x4 place as good as possible. So in most cases, you're going to end up with something highly pixelated. But if you blur it, then you know that every pixel in this image does contain at least like a certain variation of its surroundings, right? Of its previous surroundings. So this is what the template matching algorithm is. Now let's go to Hog, right? So Hog provides us a better way of representing images, right? So just remember that Hog is not just here for like object detection, so it's an image descriptor. We can use it for object detection by adding some SVM on top of it. So histogram of oriented gradients was first used to detect or describe a person using just one global feature, right? Later on, we will see how we can improve it or basically use it for local features. But for now, we're using it to represent a global feature for the whole person or for the whole image, right? So a person is represented by a single feature vector, which is later on just classified using support vector machines. Let's go skip a bit of these parts. So remember, we pre-processed the data, all of it into the same shape. Why exactly this shape? Because the original authors worked on this shape, so just representing their work, but you can, of course, improve this however you want. And then they basically split the image into 8x8 pixel cells, and then they compute the gradient vectors. How do they compute the gradients? Basically using what is it called? Sobel or some filter like that, right? So remember, by passing the filter, we can calculate the gradient in the X direction, the gradient in the Y direction, and then we can combine these gradients together. So then we create a 9-bin histogram from the 64 gradient vectors. This histogram would look something like this. Here we have the orientation or the direction or the orientation of the gradient. And here we have its intensity or its norm, let's call it like that, right? I forgot how do we call this for the gradients, but yeah. So basically it's just like the length of the vector, of the gradient vectors. Nice. So once we basically did that, again, this is how we calculate the horizontal and vertical gradients. We combine them and calculate basically the gradient magnitude and orientation. So we have this kind of matrices for just one for one of these pixel cells. And then we take the gradient direction. For example, in this case, it's 80. What we do, 80 is a simple one. So we put 2 in this case, or we add 2 to what was the content here previously. In this case, we have 25. So you can easily see that there is no like bin for 25 exactly. That means we will be sharing this 4 between the 2 bins that are closest to it. So 30 and 10. So once we have this basically a histogram, yeah, something like this. So this is a histogram of values. What do you think of a histogram of values? It's just like this. So it's just a vector, right? Of values, right? A vector of different magnitudes. So this is what a histogram is, right? So always have the same, these numbers are always the same, these bins are always the same, so we no need to save that information, but the only information we use to represent this histogram is basically the magnitudes in each bin. So this is what we get from this step. We get a vector that represents the gradients in that location. After that happened, we normalize the gradients, but we normalize them not only on the same, or we normalize the vectors in general, not only on the content of the cell which we are working on, but we normalize them based on their kind of surroundings. Why do we do that? Mainly to fix the problems with lighting variations. So normalizing, again, I'm sure you are already familiar with it. So we take a vector like this, the norm of this vector. So this is the second norm of this vector. It's simply the square root over its over the sum of its individual components squared. So a normalized gradient would look something like this. So just divided by k. And if we calculate the norm of this gradient, we will find, or we calculate the k, we will find it equal to 1. So this is the normalization point. After we finish the normalization, we get the features for the complete image. Basically, this is our features. And then we send the features for classification using SVM. Just like a small recap for what SVM is, right? So imagine we have classes here. Right? And we have the second class here. So we can see that these two classes are highly linearly separable. So we can say, let's say this linear model does separate them very well, and it gives good results. And this linear model also does the same thing. SVM tries to find the best linear model that kind of makes the highest margin between them. So the linear model itself is this one, and it tries to keep as big of a distance between these two classes as possible. So this is what SVM is. This is what SVM does. So it's a very linear model, and it could be like improved to a non-linear model by changing basically the kernel. I will not go to detail on how like the kernel looks like. Basically, you have multiple kernels such as RBF and like polynomials and stuff. All of these kernels can make that what is it called, vector multiplication from like just point like just multiplication and summation into something a bit more complicated, right? And that would allow you to build kind of a hyperspace where the data is linearly separable, even though in the original hyperspace it was not. So now we've finished with SVM. Let's go to what contouring is. So this is just like a bonus part of our course. So contours are a different way of doing what we have been trying so far. So for example, edge detection, we have tried, what is it called? Thresholding, and of course, like segmentation, we call it thresholding. And we have tried basically to do object detection. So now another part would be to do these contours, which is similar to edge detection, right? So a contour can be explained simply as a curve joining all the continuous points along the boundary, having the same color or intensity. So just trying to join the same object inside that contour. So contours can be very useful to do shape analysis, object detection, or object recognition, right? So there are two types of models. So there are parametric active contours, and there are geometric active contours. So of course, similar to what you had in machine learning, right? So parametric and non-parametric models. The first model we will speak about is the snake model. So the snake model simply tells you like this. So you have an object, say this is our object of interest. What you do is you start by building, like initialize something manually of what the boundary should look like. And basically this one will try to work as a snake and try to wrap around this object, right? So basically it will continue going forward until it finds an object with all similar color intensities, right? So basically it's trying to wrap around this or shrink wrap around the object. But the problem with this one is first, it fails to detect the concave boundaries. So basically something like this one, we start here, it will shrink, 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 shrink. But when it comes here, it will not continue like this, but it will stop basically. And the initial contour must be in general very close to the true boundary, or else it will converge to the wrong result. So this is something also very bad about this model. So the idea of going from outside and shrinking was kind of bad. It didn't really work very well. So we tried to improve, or they tried to improve this one by going the opposite direction, right? So going from the start or from the center of the object and just trying to expand a bit until we fit the object as a whole. So basically we start here. So this is our initial contour. And then we just keep on expanding it like this one until it basically surrounds the whole, what is it called? The whole object. So something very similar to what DBScan does, right? So yeah, so same principle as the snake. This one, instead of shrinking, so this is called the balloon model. So the balloon model expands and introduces, makes it possible to find the contours of an object by placing the initial snake inside the object instead of outside, while also providing more stable results. One of the bad problems, again, is that you must always provide the initial contour. So this is something that could be a bit bad. But in cases where, for example, you're trying to extract, like you're working on, you're editing an image and you're trying to extract the human being inside this image, so you're definitely not going to try and do this by hand, to build the contour by hand. So having such an algorithm that does this task for you, just basically you do this and it will perform the whole task for you, is definitely still quite useful and saves you a lot of time. Now the final model is considered the one that works best. So it's basically very similar to both initial models, but instead of working directly on the pixel intensities, now it's trying to, it's being guided by the gradients vectors, right? So basically it's looking at the gradients. Remember what gradients give you? So the gradients give you the easier detection of the boundaries, right? So remember, we have been using lots of gradients models, either the first gradient with local minimums and local maximums, or we have the second gradient with crossing the zero, right? So basically gradients allow us to detect boundaries much easier, hence an algorithm that's trying to basically find the contour that is embedded with this knowledge of where the edges are. That's definitely going to get better results. So if you'd like to do more reading about these things, this is some of the proposed reading. And for this lecture, we have finished. Do you have any questions about this lecture in general? So basically, everything we have seen today, we have seen the simple algorithm of connected component labeling, which is just like, you can think of it as a clustering technique, right? And then we have seen object detection using template matching. We have seen how to improve this one and make it work invariant to the scale using image pyramids. Then we have seen that image pyramids still do not give good results if the object has changed a little bit. So for example, if the object is rotated or something like that, or looked at from a different point of view, or if the object basically is a different type of the same class. So let's say we're looking for a dog. If we change the class of the dog, or we change the race of that dog, definitely image pyramids or template matching are not going to work. So we've seen another improvement, which is called the histogram of oriented gradients. Now, this histogram of oriented gradients does need or require some training data to train it, basically, yeah. But template matching only requires one image per class. So this is like a big difference between the two. histogram of oriented gradients, as we have seen. So basically it splits the image into different parts or 8 by 8 parts, and then basically calculates a histogram of oriented gradients, right? So basically this histogram is only a vector where each bin or each cell represents how many or represents the intensities or the amplitudes of the gradients in certain orientation, right? So we calculated the orientation of a gradient. Let's say it's 20 degrees, then we go to the 20 degrees bin and we add the intensity or the amplitude of that gradient. In the end, we end up with a very big vector that kind of represents all the gradients in their directions and their amplitudes inside the image. So later on, what we do is simply apply SVM or support vector machines, which is a linear model that can be improved into a nonlinear model by using some nonlinear filters. And we use that one on the vectors of the training data in order to build like a simple classifier. Final part was speaking about active contour models and how are they related to edge detection and how can we perform them using either the snake method of wrapping around the object or the balloon method of expanding into the object, or by using the gradient-based approach. So do you have any questions about this lecture so far?
Yes, could I ask the question about how we normalize the gradients in the concatenated histogram of 4 vectors inside the block?
Okay, yes.
So we've got, after the concatenating 36 vectors, components, and we divide it like by what? Because in the slide of 55, you just show us how we normalize one vector, but how we perform normalizing in this case. We're adding up all the same components.
Wait a second, let me just open it up. Here we go. Okay, sorry. Yep. Yeah. So the normalization of the gradients, as we said, is not applied only on one block. So basically it's applied on the block and its surroundings, right? So for example, here we are normalizing Y because we want to make it less affected by the lighting variations. And rather than normalizing each histogram individually, we're going to normalize them in blocks of 2 by 2 cells, right? So remember, this one cell in here contains its own hog, right? Or a histogram of oriented gradients, contains its own vector. This one contains its own vector. This one contains its own vector, and this one contains its own vector. So how many vectors in total do we have in this block? 4.
So 4?
Yes. So what we're going to do is the following. Remember, how many bins or what is the size of every vector?
9.
9.
Oh.
Nice.
Yes, 9.
Let me see, 1 second. So what we're going to do is, in that block of 4 by 4, we take the 9 values here, 9 values here, 9 values here, 9 values here, and we normalize them. We put them in the same vector first, like we concatenate these 9 by 9, these 4 by 9 vectors. We make them into the same one-dimensional vector, and we calculate their norm, so the norm of their concatenated values, and we normalize all of their values using that norm. Does that make a bit more sense?
Yes, now it's more clear.
Okay, nice. Thanks a lot for the question. Definitely, it's very nice to understand where this 36 came from, right? Anybody has any questions? Anything else? If you don't, then we are certainly going to have a final revision right after this next lecture, so no worries, right? So this lecture, no, yeah, this one. Nice. So this lecture is about image features. How can we extract image features? How can we describe features inside an image? And definitely, what are we going to use? What are we going to do with them after we do that? So this lecture is definitely going to be a pretty lengthy one. So we might not finish everything today, and we will definitely have it either during the next lecture and the next week too. So let's get started, right? Yep. So the content that we will be seeing, so basically just a small introduction to what are these image features. We will speak about these feature detectors, such as the Harris detector, the Shi-Thompson detector, and the lower detector or SIFT. And then we will be speaking about feature descriptor, so not just a detector, so basically a descriptor, which is basically SIFT. So basically we will be speaking about SIFT again, but you will see that SIFT contains two at least parts, one for the detection of the feature and the second for the description of the feature. We will speak what is a feature in general, of course, later on. And then the final part would be feature matching, right? So just so we can get an idea of what feature matching could be used for. So imagine we have two images of the same, like the same view, right? Or the same object. And we wanted to build build one image that kind of combines both of them into a big panorama image, right? So here we see this one is the same as this one, and this one is the same as this one. So basically we can technically combine them and have something that contains something like this, right? So this is what we want. What we do is we just build these or detect interest points, or basically a point that kind of represents the object. So these are the points that are interesting inside the objects. And what we do, we extract vector feature descriptor surrounding each interest point. So basically we go, this is an interesting point, this is an interesting point. We take like a window around it and kind of describe it. How can we describe an image, right? So this is a very good question that I want to ask you guys right now. So take an image like this or a cell like this, how can you convert it into a vector that can describe it in some way?
For the simplest case, we can just flatten it, like concatenate all the rows.
Very good idea, but I want something a bit related to what we just saw, like just not even like 2 minutes ago.
Like we can go through all the picture with maybe 2 by 2 or 4 by 4 block and find representative points inside these blocks.
So remember how Hog works? Yeah, we're not going to be applying all of the Hog algorithm. So we're not going to split all the image into these 8 by 8 pixels and format it and do all of that. Simply, we will take one window around an interesting point and describe it very similarly to Hog, right? So basically what we can do is we can build this histogram of oriented gradients for this window that we are interested in. So here, for example, is gradients of 10, this is 20, this is 30, this is 180. And then we put the amplitudes of all these gradients, and ta-da, you have yourself a vector representation of the content of this window that you are interested in, right? So this is one way to basically describe the surrounding of this so-called interesting point, right? Once we have the descriptions of these interesting points, what we can do is simply build this correspondence between the points in here and the points in here. And from there, we will have just a simple calculation or a simple algorithm that joins both images. And ta-da, there we go. Of course, we must apply some sort of linear or affine transformation to the image in order, or to the two images in order for them to like match exactly. So how can we do this task? I will send you guys a simple, or where can we use this algorithm. I will send you a simple video. Probably you might not be able to watch it very well on my window. Oh, weird. Nice. Let me. So I'm going to send it in here, and everybody just can watch it locally. So this is called VSLAM. I'm not sure if you can you hear her voice?
No.
You cannot hear her. Huh? Yeah. So just basically try to open up this video locally. So what she's trying to do is to build basically a robot that can understand its surroundings from these images, from just images, right? So understand its surroundings, build some sort of a 3D model of its environment, and be able to basically understand where he is or what is he looking at inside that environment based on that map. Right. So here is what he's doing. So basically he's trying to look at the image, find the features or find the points which are interesting, these key points, which are interesting in his point of view, and then basically describe them using the HOG or histogram oriented gradients. And then from there, he would just go around, explore and explore and explore and build this map of the space where he is in. Once he has that map, he can easily just look at a new position and compare it with the map and understand where he is located at. So here you can see that he was able to kind of reconstruct some sort of a 3D representation of the surroundings or of the images he was looking at. So he was able to at least find the shape of the house he was looking in. And this is definitely something that you could, like, for example, implement in a Zumba or Roomba. Yeah, in Roomba. Like those robots that go around your house and clean it. So basically they would need to first understand what is your house and where can they move. And then from there, they would just walk around and clean up as much as they can. So yeah, let's continue. Yeah, you can watch it a bit later on. It's pretty useful. Could give you some ideas. So first, let's speak about these feature detectors. So first, we will speak about the Harris detector, and then we will speak about SIFT. If we don't have enough time to basically cover SIFT, I think we have. Okay, I think we have. Yeah. Yeah. So let's go. Let's start with the Harris detector. It's a very simple detector, right? So the basics of this detector is this question: what makes a feature or a point interesting? So here, is this place interesting for you, right? All of this. There's nothing much happening, right? So it's kind of the same. Here it's also kind of the same. What is interesting for us is something or these edges, right? Edges are quite interesting, or edges are quite useful. So for example, we had an algorithm before that does these edge detection and stuff using gradient calculations. Now we could try to see how we could maybe improve this a bit further to be able to define not just edges, which are of course important, but also corners, right? So this is the goal of this algorithm. It's to kind of improve over edge detection by detecting not just edges, but corners also, and being able to differentiate between them. So here we have a flat region, no change at all in all directions. Here we have an edge. So here there should not be like no change along the edge direction, but certainly there is a change from what's here to what's here, right? And here we have the corner where basically everywhere you're looking, there is a certain change, right? So this is what the Harris corner detector does. So again, Harris is for corner detections, as we said. So you can see that it was able to basically, you know, let's try to build this concave map, kind of build a segmentation of this object, right? So it's kind of similar to what we have seen before with edge detection, but now we're no longer interested in all the edges. We're just interested in the most interesting edges, which are corners. So this is how its results would look like. Simply put, what it does is basically tries to calculate how much change are we having in a certain window. So say we have a window, for example, here. Yeah, this is the window. So this was the original window that we are looking in, and we're trying to find out, so this is the center of that window, right? We're trying to find out if this point or this center is interesting or not. So what we simply do is we just, yeah, like this. No, let me use a different kind of visualization, like this. So say this is our window of interest. The center of this one is the point which we're trying to compute if it's interesting or not. What we do, we build a variety of these other windows surrounding our window, and we try to calculate basically the pixel by pixel difference and basically sum it, right? So what we will do is we will calculate MSE between this window and this window. Since they have the same size, then basically it's just a pixel by pixel difference. Then we just square them so we don't have negatives and positives influencing each other. And then we just take the sum, right? Very simple. So this one would give us some sort of an estimation of how much change do we have in an image, right? But this estimation is only in the direction UV. So we must specify this direction UV. If we want to get an estimation with all the directions, so basically we will have to iterate over UV in all the different values that we can have. So basically UV could go from just a simple vector like this to something small, something much bigger, something much bigger, something in this direction. So there's definitely a lot of calculations to be done here. So the limitation of this one, it's very slow to compute for each pixel and each offset. And itself, it's quite difficult. So I hope you guys are familiar with the Taylor series expansion. Can somebody tell me what do we use this Taylor series expansion for?
Derivatives of different order.
What is it used for?
To find the nearest value in this point, like we try to calculate what it will be function in the neighborhood of concrete point.
Okay, got you. So basically what it's trying to do, it's basically trying to use the derivatives of the function in order to estimate what the function would look like outside of the point of interest, right? So at a certain point, we're trying to estimate any function we want using a polynomial. So of course, this is not what a polynomial looks like using a polynomial, let's say. The simplest form of polynomials is definitely a linear function. So what we're trying to do is we're trying to estimate this super non-linear function using a linear estimation. This linear estimation is of course coming from the Taylor series expansion. So here we will have, so here we have the function at the point. So if we want to get the value of what the point is or what the function is after a certain, let's say this is x. Let's build the function. So this is the function. This is what the function looks like in this point. What we're trying to do is we're trying to build a line like this one that allows us to basically do the following. So this is x plus h, right? We are trying to estimate the value of the function at this x plus h position using only this linear model, right? Of course, the higher or the further away from x we get, the more useless this estimation is, right? So here, this estimation will give us something like this, but in reality, the value of the function is much bigger. So this is what Taylor series expansion does, and we are trying to limit it only to the first order approximation, which is kind of good enough if your UV vector is small enough. So basically, yeah, here we will have all the those polynomial terms of the Taylor series expansion, but for us, they're just, oh, right. So they're just higher order terms that we will neglect for the calculations. So overall, this I of x plus, so I means the intensities in surrounding basically this center point. So this was x and y. So this was position xy. So uv was like this, for example. This is x plus u, y plus v point, and this is I of x point, x plus u, y plus v point. So yeah. So basically it's represented using the value or the intensities surrounding the original pixel plus the basically the what is it called? The change in the x direction multiplied by u plus the change in the y direction multiplied by v. Basically, the further away, the more different it is. If it's closer, then it's going to be more similar because this number would be smaller. And of course, it's going to depend on the change overall inside the image or inside that region. Nice. So to show in shorthand, just we're going to represent I of x as the derivative of I with regards to the x direction. Again, just a small reminder. How do we calculate derivatives in images? Do we use some complicated function derivative, or we just send out a simple what is it called? Kernel.
It's like kernel with 4 in the center,
Yeah.
and ones around this, like
I like
above,
it. You are
from left, right?
Right. So yeah, that's one way to do it. Of course, there are different things, different ways to do this one. So that's a very good way to do it. And there is the, of course, Laplacian of Gaussians, basically where it blurs first the image and then applies the kernel that your friend has just spoken about, right? So there are many ways to do the calculation of the derivative, but all of them end up being just a simple convolution with a certain kernel that we define its weight. So calculating these derivatives is kind of easy. So now to go back to the original image or to the original formula that we wanted, and we simplify it using our, what is it called? Taylor series expansion. So here we simplify it using the Taylor series expansion of this term, which is basically I of xy plus the change in the x direction multiplied by u, this is u, plus the change in the y direction multiplied by v. Of course, minus I of xy still is the same. Why is this pretty useful? Mainly it's because it will simplify it for us, and these two will disappear. And what we will end up having, something like this: the sum in the of I x multiplied by u plus sum over plus this I, the derivative of I in the y direction multiplied by v. So already this is a bit simpler, but it's still kind of difficult to calculate. So let's simplify it even further. So let's open up this term, right? Imagine we have, sorry, annotate text. So imagine we have this A, sorry, A plus B squared. What is it equal to? Go ahead, help me out, guys.
A squared plus B squared plus 2AB.
Thanks a lot. There you go. So this is the formula, right? So basically, we're gonna have a term with u squared, a term with v squared, and a term with 2uv, right? Now, what these terms are, just for like simplification, we name them as A, B, and C. So for simplification, we will denote them as A and B and C, but in reality, it is simply the following. So basically, we did 2 steps in this direction. Huh? So here, let's do it slowly. So I xu squared plus I y v. Let's do squared here. Y v squared plus 2 multiplied by I, sorry, x I u I y, yes, u v, right? And we still have the big sum in here over all of this. You know that the sum over you could introduce this sum inside each one of these 3 terms. So basically, we will have the sum over this term, the sum over this term, plus basically the sum over this term, plus the sum over this term, right? Now that we have this, we just take, since this one, the, what is it called? The u squared is not dependent on the content of the sum, meaning we could kind of take it out and multiply it with u squared here, u squared. So are you familiar with this one? Like I equals A, the sum of over I, right?
Yes, yes.
Nice. So this is what we basically just did here. And we simplified it to get exactly this one. So it's the sum over intensities over the x, the derivative of intensity in the x direction squared. B is equal to the sum over the I, or the derivative in the x direction multiplied by the derivative in the y direction. And C is equal to the sum of I squared, right, over the y. So very simple, very basic workaround. So just to simplify this even further, so we can definitely see that this is what is it called? The squared form of some vector. And we could represent it in this following direction, right? Where we have UV in here, UV in here, and here we have the matrix, or the matrix that kind of defines the values of this, what is it called? The thing on the second power of 2. You got it right. So this power of 2 operation, right? So A squared, yeah, the squared. So this is the matrix squared form. So this is how we represent basically an ellipse equation. And these are what kind of represent, so given a UV vector, this is how it would look like inside the ellipse. Just so everybody knows what an ellipse looks like, I think we have it already here, right? This is a circle. This is an ellipse. I cannot rotate it a bit further like this. Yeah, you cannot rotate this one. Let me just draw it then normally, like this. This is what usually ellipses look like, right? So we have this axis and we have this axis. These are like the two ways, important things of representing an ellipse. I think you have already seen this or something similar to this one when we were studying PCA, right? So remember PCA, you had like data like this one. And what you were trying to do, so basically this was your initial ing, how do you call this? Space, let's call it space. I forgot the name of it, but yeah, this is a space, Euclidean space. Kind of forgot it, but yeah. What we're trying to do is basically build a mapping from this space into something or like an affine transformation where the variance, right, in this direction is saved as much as possible, and the variance in this direction is as small as possible, right? Or let me just go back. And basically you were able to build this, what is it called? Eclipse or ellipse, yeah, ellipse. So again, just for simplicity, we are putting back what A, B, and C are, in fact, but we don't really need them in like this. So all of these values are easily calculatable. So this is something that you could calculate using kernels. This is just something that also kernel, kernel, and then multiply, kernel, kernel, and then multiply, or the same kernel and then multiply. So what Harris-Corner detection does, so basically we calculate this H matrix, and then from there, we will calculate its eigenvalues and its eigenvectors, right? So the eigenvalues, what do they give you? It's the amount of intensity change in the two principal orthogonal gradient directions. Let's go back. I don't think we could go back. Let me try. Ah, yeah, we could. Here it is. Yeah. So remember when we had the data looking like this, and we told you using PCA, we managed to build this ellipse around the data, let's say. Now, can you tell me what this represents, what these two represents, or how do you find PCA? Right? So you calculate the eigenvalues, eigenvectors, and then you take the top vectors which have the highest eigenvalues, right? Do you remember?
Yes, yes.
Nice. So eigenvectors, eigenvalues. So yes, this is the first eigenvector, second eigenvectors, for example, and the value of the eigenvalue represents a very interesting concept, which is the intensity or the change in this direction, right? So the intensity of change in this or in the direction of the eigenvalue. So this is what the eigenvalues give you and the eigenvectors give you. So they reveal the amount of intensity change in the two principal orthogonal gradient directions in the window. So given this matrix, what we will do is simply calculate its eigenvalues and its eigenvectors. Now, to give you like a small revision on what or how to calculate eigenvalues and eigenvectors, we will do a simple example, but before that, I think I would give you a good link. Yep. We will speak first about the determinant of a matrix. What is the determinant of a matrix, right? So determinant of a matrix is simply, it helps you find the inverse matrix of a matrix. It tells us about the matrix that are useful system of linear equations and calculus and so on and so forth. So the symbol, which looks like this, or like the determinant of the matrix, is calculated in a simple manner. We will only be working with 2x2 matrices or 3x3 matrices. So let's look at how they're done. So here the determinant of the matrix is A multiplied by D, minus C multiplied by B. So remember this shape. I'm sure you're already familiar with this one, but it's nice to revise it. So this is how you calculate, what is it called? The determinant. So again, positive, negative. Nice. Now for the 2x2 matrix case, it's pretty simple, but for the 3x3 matrix, it's gets a little bit more complicated, but it's still simple. So A multiplied by the determinant of this minus B multiplied by the determinant of this plus C multiplied by the determinant of this. How do you define? So basically, yes. So A, B, C. The second one has a minus, third one has a plus, fourth one has a minus, fifth one has a plus, if they exist. And what you simply do is you cross, and take the derivative of what take the determinant of what is left. Here you have a 2x2 matrix, so it's simple. So this one multiplied by this one minus this one multiplied by this one, right? So just try to remember, how do you build this formula? Of course, this formula, you're not going to remember it. There are too many terms and it's quite ugly, but just try to remember the pattern. A multiplied by the determinant of what is left minus B multiplied by the determinant of what is left. And how do you define what is left? Just draw these numbers or these lines, and basically it will tell you what is left. There you go. Now that we have this like kind of revision, right, real quick, I'll send it to you in the So again, for the purpose of this course, we're only going to be working with vectors or matrices of 2x2 or 3x3. So let's continue. How do we calculate first the eigenvalues, and then from each eigenvalue we'll find its corresponding eigenvectors? Simply the determinant of A minus lambda I. I is just, it's not the intensity matrix as we've seen before. I is the, well, basically identity matrix, right? So 1, 1, 1, 1, 1, 1, 1, and everywhere else we have zeros. This is what I is. Equals 0. So we're trying to solve this equation in order to find the different values of lambda. Here we will have a simple example, basically where each one of these multiplications is 0, or these values is 0, which makes it very easier to do the calculation, right? So let's do it together. Minus 1 multiplied by the determinant of 3, 4, 0, 7 plus 2 multiplied by the determinant of 0, 0, 4, 7.
Should it be minus 2?
Yes, minus 2. Thanks a lot. Yes, thank you. And yeah, minus 2. So plus, minus, plus. Minus 2 multiplied by basically what's left, which is 0, 0, 4, 7. And then plus 0 multiplied by the determinant of what is left, which is 0, 0, 3, 0. So here we can see 0 multiplied by 0 minus 0 multiplied by 3 is equal to 0 multiplied by 0 is equal to 0. This one disappears. Minus 2 multiplied by 0. 0 multiplied by 0 gives you 0. Minus 0 multiplied by 4 gives you 0. 0 minus 0 is 0. 0 multiplied by 2. This one disappears. So basically you end up with minus 1 multiplied by, why is this 2? This is 3, right? Yeah, 3. So basically 3 times 7 minus 0 times 4. Uh, 0 times 4, how much is that? 0. Minus 1 times, oh, this one is a big number. I don't know. How much is this? 3 times 7.
21.
21, thank you. So minus 21. And very well, that was the determinant of this matrix. So just a small example. Yes, let's now do the determinant of the real matrix that we're interested in, not just this one, which is -1, 2, 0, 0, 3, this original matrix, minus lambda, so lambda is our variable, multiplied by the identity matrix equals 0. So basically we put lambda here, lambda here, lambda here, lambda here, lambda here. Simplified, it gives you this one, -1, -1, minus lambda, 3 minus lambda, 7 minus lambda, and the rest, they stay the same. And then when you're calculating the, what is it called? The determinant, as we have seen before, the majority of the terms disappear, and you have -1 minus lambda multiplied by this determinant, -2 multiplied by this determinant, which disappears because of the zeros, plus 0 multiplied with this determinant, which disappears because of the zeros. So in the end, we have just a simple function like this. And you can see that the answers are quite direct. So here, lambda is equal to 7, or lambda is equal to 3, or lambda is equal to -1. All of these values will give you the function equal to 0. And there are your 3 eigenvalues. Simply put, after that, you just replace each lambda in this, what is it called? In this formula, and then you solve a system of linear equations, right? So basically you put A, you put lambda minus, and then you have the X, solve it for X, and this is your vector or your eigenvector. I'm sure you're all familiar on how to solve a system of linear equations, like you did this in like middle school. So it should be something quite easy, like with this replacement method, remember. Now let's go back to our Harris corner detector and how it's going to use these eigenvalues, which we just remembered, how it's going to use these eigenvalues of this H, what is it called, matrix, in order to basically do some calculations. So again, H kind of summarizes to us the change in each direction, right? So basically H, so this one is the first eigenvalue, and this one is the second eigenvalue. And this kind of tells us about the differences, or what are the orientations, or what are the gradients inside this patch, right? So it's telling us how fast, or what are the changes here inside this patch. So for example, from this place to this place, there is a high change. From this place to this place, there's a high change. Let's say that it's looking like this. So basically it should, there are many changes in all directions and stuff like that. So this can be summarized using the eigenvalues and the directions of their eigenvectors. So here we have lambda 1 and lambda 2, which are the values of eigenvalues of H. This is how we're representing them. If we had lambda 2 much bigger than lambda 1, meaning there is change in one direction, but the other one there is nothing, right? So meaning this one is an edge. Same thing if we have it lambda 1 much bigger than lambda 2, meaning again it is an edge, but like the opposite direction, so either this or this one. If both of them are very small, meaning there is no change in either direction, right? No change in either direction means it's a flat region, or a point that is of no interest for us. Remember, we're only interested in corners. So here we have the edge one, we have the second type of edges, and here we have the flat regions. And we're only interested in the cases where both lambda 1 and lambda 2 are very large. Of course, they can be not the same value, so they're quite different from each other, but they are much larger than a certain threshold. How can we simplify this even further, right? So basically what we want is a certain measure or a certain combination of lambda 1 and lambda 2 that rejects all of these. So basically something like this, right? So if we want a classifier like this. Sorry. Yeah. So again, based on the H matrix and its, what is it called? It's, help me out. Its eigenvalues, we get the following, right? So the determinant of H is equal to lambda 1 and lambda 2. You can prove this one since it's like a symmetric thingy, easily replaceable, and just by replacing the A, B, and C and D, you can get that. And here we have the trace of H, which is lambda 1 plus lambda 2. Simplify this equation a bit, and you will have the following, right? So lambda 1, lambda 2 minus alpha of lambda 1, lambda 2 plus squared. So let's think about what it really is, right? So if lambda 1 is super small, meaning we will have something here in this, so let's say 0.1 multiplied by, let's write it, yeah. The first case, which is one of them, is super small, 0.1 multiplied by, let's say, 9 minus alpha, a certain alpha, multiplied by their sum, which is 9.1 squared. Yeah. 0.1 multiplied by 9, so this gives you 0.9. And 9.1 to the power of 2, this gives you a very large number, let's say 100. I'm sure it's not 100, but let's say minus 100, right? So this gives you a negative value, right? So when one of them is small, then the squared sum is much bigger than the multiplication. When both of them are big, then these values, yeah, basically, let's say, when both of them are big, then the multiplication becomes much larger than the sum squared. So for example, 9 yeah, wait a second. Wait a second. Yeah, let's take it, for example, 90 multiplied by 99 plus, say, 100 minus alpha multiplied by their sum squared, which is 190 squared. So in this case, we have the following. This one is a very large number. This one is certainly a bit larger than this one, but with the alpha, alpha is usually something that is very small. So with the alpha, this one decreases again, and you have at least a positive number. So this is what this function is trying to do. Of course, this function is pretty complicated, and there are so many edge cases where it doesn't work. So this was the initial proposal, and then it was improved or simplified much further on. So this is what basically the function is trying to do. Corners now will have a r that is bigger than 0. Edges will have an r that is smaller than 0 in the case where one of these is too small. So basically, as we said, the sum will be much bigger than the multiplication, or the sum squared much bigger than the multiplication. And if it's a flat region, then both of them are small. So 0 multiplied by 0 minus 0 multiplied by 0. So it's still 0, still something very small. Alpha, again, it's something that is very empirically found. Basically, you try different alphas, whatever works best for you, you use it. Usually you could have something about 0.05 or 0.005. So here now we have like the characteristics of what's a good function. So R depends only on eigenvalues of H. R is a large value or large for a corner. R is negative with large magnitude for an edge. And R is, or the amplitude of R is small, or the value, absolute value of R is small for a flat region. So here is the Harris edge detector, as we've said, not edge detector, the corner detector, as we have seen before. So it's certainly quite good. It's able to find points inside the image which are quite interesting. So for example, all of this blank space was completely ignored, and all of these points are taken into effect. So here, definitely a bit of a problem, but not something too harsh. So here we have the corner response. Remember the R for every pixel, right? So here we see the blue ones, they're useless. The red areas are kind of the interesting parts of the image. And here we have the thresholding. So if R is higher than a certain threshold, still we can manage to see the shape of the object again. After that, we do the non-maximum suppression. So non-maximal suppression, as I said, it's an algorithm. Basically what it does, let's go back. Here. So basically it takes, for example, this point. This was like the highest point in R. And then what it tries to do, it looks around this point. All of the points around it, it will basically remove them, right? It will keep only the highest value in this area. And then it will keep only the highest value in this area, keep only the highest value in this area, keep only the highest value in this area. Same thing here, same thing here, same thing here. How does it define an area? Simply using a window, right? So it basically walks around, putting windows on the image, and then just basically take the highest value in that window. This one there is the result of the non-maximal suppression. We will speak more in detail about non-maximal suppression because it's kind of related to some concepts that we will speak about in object detection and some metrics that we will speak about in object detection. So it's for now, just remember the algorithm as what I have described to you. So this is how the Harris features look like. These are the values after non-maximal suppression. And now they wanted to build like some sort of extension, right? Or an improvement. So remember when we were trying to improve those Laplacians for calculation of the second derivative, right? So Laplacian is used for calculation of the second derivative. We tried to improve that further by using the Laplacian of Gaussians, right? So Laplacian of Gaussians, or like this Mexican hat, allows you to basically blur the image and then calculate the second derivative, which kind of gives you something a bit better than just calculating the second derivative directly. But in this case, what we're trying to do is we're trying to improve again over the values of this one using something very similar to what we have done, which is like this Gaussian thingy. So previously we were saying whether like this, if you belong inside this window, we consider your value, right? So we have this, here is the window, the central pixel of interest. If you are inside this window, we will consider your values for the calculation of how interesting is this point. If you're not, then we don't consider you. We could improve this further, so like this, by taking basically, this is the central point, and we build some sort of a Gaussian distribution around it, right? So these points will have higher weight. These points will have lesser weight, much lesser weight, much lesser weight, much lesser, much lesser, much lesser, much lesser weights, right? So this is what the Gaussian distribution would look like. Basically, it's the same algorithm as before, but now at every point, we are just giving it a certain weight. The weight in this case is a Gaussian vector. So it's no longer, what is it called? An if statement, if it's inside or not inside. It's basically a Gaussian for all the different values that exist. So definitely much harder computationally, but would give better results, as we have seen that basically the Gaussian combinations of all the other pixels surrounding it is much better than just a small location surrounding the pixel. So just to put it in summary, we compute the derivatives in the x and y direction, compute their product, remember, because for this one, compute the, compute the products here, and we compute their, how is it called? Squared, yeah, compute their squared value. And then we just compute the sum of the products of the derivative at each pixel. Remember, we've seen this here. Yeah, this one. So we compute all of these values. Yeah, and then we define the matrix at H. So we define the matrix H, sorry, like this, huh? We define the matrix H at each pixel, compute the response of the detector at each pixel. So basically, remember, the response is just a combination over the eigenvalues of H, right? And then we threshold on a value of R, compute non-maximum suppression, remove the majority of those points, and keep only those which interest us. So far, this is the algorithm that we have seen. We could improve it further by, for each pixel that meets the criteria in 6, compute a feature descriptor. So this is what we will be speaking about a bit later on in the lecture. But we have already discussed it before, so it's basically just a simple histogram of gradients. So this is just a small information about what Harris corner response is. It's highly rotation invariant. So whatever you are working with here, same thing would give you here. The direction of the eigen vectors will change, of course, but the eigenvalues themselves do not change. And this is what's important, basically, for the Harris corner response. It's also very irrelevant or very invariant to intensity changes. So basically this or this is the same. Why? Because we're not interested mainly in the value of I, but we're interested in the change between I and what is close to it, right? And this is the example of the Harris corner detection point. I think, yes, let's finish this Harris corner detection, and we will take, we'll call it, how much time do we still have? Just 8 minutes, right? Not enough time. So here we have a corner. Of course, scale does not work with it. So here we have the same window size. The corner in this case is something that has a lot of a high R value, but when we scale it much larger inside this window, it becomes just a normal edge on all of these places. Hence, it will have a small R value, or like a negative R value, right? So here, R value is much, much bigger than 0. Here, R value is much, much smaller than 0. So R is very not invariant to changes in scale. Again, somebody came up with the idea to kind of, what is it called? Instead of using this complicated formula, he said, let's just focus R is equal to minimum between lambda 1 and lambda 2. Meaning, if lambda 1, so basically we just want to ignore edges and we want to ignore flat areas, right? In all of these cases, at least one of the lambdas is small, and this is something that we don't want. So basically, it's taking the minimum of lambda 1 and lambda 2 as the threshold or as the value of response. If lambda 1 is small, lambda 2 is big, then it's an edge. We don't want it anyway, so remove it. If lambda 2 is big and lambda 1 is small, then we still don't want it anyway. It's an edge in the other direction. If both of them are small, then the minimum, of course, will be small, and we don't want it anyway. It's a flat area. But if the minimum is big, that means the other one is also big, and that is a corner. So this is a much simpler formulation of this much more complicated algorithm or formula, and it gives the same results or even better results. That's what they're saying. So we will speak about this scale invariant feature transform. It's actually very simple. I would have loved to go through it already, but sadly we didn't have enough time. We will finish it next week. For now, let's go through the previous lectures and kind of recap them into a mind map, right?
Why?
What did you say? Did somebody say anything? Anybody? Nobody said it. Okay, so I think the last lecture that we have summarized was only the first lecture. So let's speak about, or maybe the second lecture. Yeah, it was the second lecture. So the third lecture, and we go on. Just so everybody would have like a small revision. So we spoke about segmentation, we spoke about thresholding, we spoke about edge detection and how it could be used, for example, for segmentation. And then we spoke about mathematical operations such as erosion, dilation, right? And then how we could compute compound operations such as opening and closing. So seen binarization, how can it be done using thresholding? We have seen what it gives. These are the results. Simple thresholding, we have seen it. Thresholding is not easy because finding the value for the threshold is quite difficult, and finding that or finding the good threshold sometimes does not exist. We've seen that there are different segmentation methods. One is called the bimodal histogram, which looks like this one. Basically, it's based on the existence of this bimodal histogram and about the assumption that we have only two peaks in the intensities of the values. So one for the background and one for the foreground. Then we've seen how can we calculate basically the center or the point between these two peaks. And we said that we will do it using the Otsu's method, because if you split here, if you split here, the variance of this one will be too large, this one will be small. If you split here, the variance of this one will be too large, and this one will be too small. But if you split here, both of their values or both of their variances will be too small, which is something that we want. We continue. Yeah, and we spoke about semi-thresholding, where instead of putting 1 here, we put F, or we put the same value. Then we spoke about the adaptive thresholding, where we basically apply the average thresholder based on every single small region inside the image, which gives basically better results. And then instead of taking the average, now we're taking something similar to the Gaussian, where we basically focus on the center and ignore the rest. Yes, and then we spoke about image gradients and said that the image edge detections, sorry. And we said that edge detection is basically the detection of the places where the change in intensity is very high. And we said that we can find these changes simply by using the derivatives. So we saw that the first derivatives gives you local minimums and maximums around the changes in intensities. And the second derivative gives you a crossing of 0 at each derivative, or at each, edge. And then we saw that this is quite useful, but not very useful, because we have a 2D discrete function instead of a 1D continuous function. And we decided to basically, do some sort of an approximation for it. There are 3 types of approximations. Using the central difference approximation, what we're doing is we put h equals to 2 in here, and then basically we define the vector, or we define the derivative in each direction. We saw that the derivative in each direction actually turned out to be nothing but a simple filter. So basically a linear combination of the content of the values surrounding the image. And then said, let's kind of improve this a bit further by applying some smoothing into the image, and then also applying the 1D derivative filter, which gave us the Sobel filter. Sobel filter gives you 2 basically derivatives, or 2 new matrices of values, and from those we can calculate the, as we said, the direction and amplitude. There are different, again, what are they called? Edge detectors. There is Sobel, Shar, Roberts, and Prewitt. They all kind of overall look the same, but with different intensities for the pixels, right? Yeah. And then we saw how can we combine both of them, basically like this, into this matrix of amplitudes. And from this matrix of amplitudes, we just threshold it, and we can combine both horizontal and vertical edges. We saw that a Laplacian of filter also does kind of the same thing, but instead of working with the first derivative, it works with the second derivative. And we saw that it also can be represented using a filter like this one. So -4, 1, 1, 1, 0, 0, 0, 0, 0. And yeah, basically after applying this Laplacian filters, you get the edges with crossings of 0, and you get like the others with just like 0. Here is the difference between Laplacian and basically Sobel X and Sobel Y. Later on, we could combine these two images and get something a bit clearer. We saw that we could improve Laplacian of Gaussian using just a Gaussian filter instead of just -4, 1, 1, 1, 0. Basically, we just can improve this a bit further with a very large value in the center, and then the values decrease as we go further and further away from the image. So here, for example, -40, -24, -12, 3, 3, 0, something like that. So this is the Laplacian of Gaussian. So this is Laplace filter without the smoothing, without the Gaussian part. And this is the Laplace filter with the smoothing part. And then we saw the canny edge detector in general. So here it is. So the canny operator is a multi-scale algorithm designed to be an optimal edge detector. Simply, it applies smoothing to remove noise, then finds the intensity in using different 4 filters, which is the horizontal, vertical, and diagonal edges, which is just one, what is it called? A filter to detect or to calculate derivatives, as we have seen before. And then we do the non-maximal expression, and we do some thresholding. Yeah, this is what the canny edge detector's results look like. So it's definitely a bit better than the previous ones. What is morphology? So the morphology is a way to describe images using the shapes. We have seen what are structuring elements, or these kernels, right? And then we saw that erosion and dilation are 2 operations that we could build up on top of these, what is it called? These kernels, these structuring elements. So shrinking is for erosion, and dilation gives you like expanding. And we saw that basically we could combine these 2 ideas in order to build 2 more complicated things, such as opening and closing. So this is it for this for the revision of this lecture. We didn't have enough time to build or to revise the other lectures and build the mind map for the others, but I'm certainly going to do like a much larger revision for all the lectures before the midterm, so that everybody has at least the basic information. So thanks a lot for attending, and I see that we have already passed the time. So thanks for staying around, and I hope you enjoy the rest of your day.
Thank you. Goodbye.
Thank you. Goodbye.
Thank you.
Thank you so much.
Bye.
Bye.
Goodbye.
Bye-bye.